So in our previous video, we got a chance to learn what are the intermolecular forces, and now what we're going to do is take a look and see how do we actually determine the intermolecular forces in a compound. So what you would often be asked here is something like, what intermolecular forces, or IMFs, would, you know how it's supposed to be spelled, would the following, holy moly, following molecules experience? That's a really common question that somebody would ask you in a chemistry class, and then they would list some molecules, and your job is going to be to figure out what intermolecular forces do they actually experience. And so ultimately, what you need to do when you have a problem like this is you need to determine, is it polar? Because polarity is what determines the forces felt by a molecule. So the steps that you need to take is, number one, you need to draw the Lewis structure, which should not surprise you because that is what we have been doing over and over and over again. After you've done that, you should find the geometry, because then you can use the geometry to determine the polarity. So find the polarity, determine, is it symmetrical? Is it asymmetrical? Look at the bonds and see what's going on. And then the last thing you need to do is determine the intermolecular forces. Once you know if it's polar or not, then you know what intermolecular forces would actually exist in a molecule. So let's work through this example of POCl3. So to draw POCl3, you'd want to find out how many valence electrons each of these atoms has, and then you'd want to use that to find out how many valence electrons in total are in this molecule. So in this molecule, we have 7 coming from the chlorines, and we have 3 chlorines. So that's 21 plus 6 plus 5. That gives us a total of 32 valence electrons to work with. So then the next thing we want to do is determine, what is our central atom going to be? Well, phosphorus has the most unpaired electrons, so phosphorus is going to be your central atom. Then form your bonds to your other elements around the outside of your central atom. Add your lone pairs around, actually count up your electrons that you've used. So we used up 8. That leaves us with a total of 24 left. Add those electrons around the outside, around the outside, around the outside of your terminal atoms. And then you would do the same with oxygen. Don't do this in pen, because I'm going to show you why this is wrong, right? Then you would notice, okay, I have phosphorus in the center. I need to check my formal charges. Phosphorus brings 5 valence electrons, surrounded by 4 dots and dashes, has a formal charge of positive 1 in this structure. Oh. Oxygen has 6 valence electrons, but is surrounded by 7 dots and dashes. So that means oxygen in this structure has a -1 as its formal charge. And chlorine has 7 valence electrons and 7 dots and dashes, so they all have formal charges of 0. Okay, so that tells us our chlorines are happy in this structure, but the phosphorus needs another electron. The oxygen needs to move 1 electron. So what do we end up doing? We end up forming that double bond. So phosphorus is double bonded to oxygen, and then it has the chlorines that surround it like this. So there we go. That's our structure for POCl3. And then we need to figure out, what is the geometry. So remember, the electron group geometry is just how many groups surround it. Well, there's 4 groups that surround it, so that makes it tetrahedral. Tetrahedral. Boy, I'm struggling with writing today. Okay, and then molecular geometry is actually going to be the same because there are no lone pairs that surround that central atom. So it is also tetrahedral. There we go. Should have just wrote tetra, you know what I mean. So then we need to look, is it symmetrical or asymmetrical? Well, it has a different atom on one side of this molecule, which means it's asymmetrical, which tells us this is a polar molecule. So now we need to think about intermolecular forces. That's an I, but not an E. Okay, so intermolecular forces. Let's think about them for a second. We have a bunch of different intermolecular forces. Number one is you had London forces. So what experiences London forces? Well, everything. It doesn't matter if it is polar or nonpolar. If it is a molecule, it experiences London forces. So this molecule has London forces because everything has London forces. The next one I want to think about is dipole-dipole. What experiences dipole-dipole? Well, only polar molecules. Has to be polar or else it does not experience dipole-dipole. Next would be hydrogen bonding. So what experiences hydrogen bonding? It has to be polar and H must be bonded directly to oxygen, nitrogen, or fluorine. The only other type here is ion dipole. And the only way you have ion dipole is you must have a polar molecule and an ionic compound. That's the only way. You actually have to have a mixture in order for there to be ion dipole forces. So let's think back to what we have. We know there's London forces because everything has London forces. Just always write London forces down. But we also discovered it's polar because of the asymmetry in this molecule. It doesn't have hydrogen. So it doesn't have hydrogen bonded to oxygen, nitrogen, or fluorine. So it doesn't have hydrogen bonding. But it is polar, which means it does have dipole-dipole. And it doesn't have an ion because it's not a mixture, it's just one substance. So what this molecule would experience, if you just had like a container of POCl3, it would be able to experience London forces and dipole-dipole forces. So now that we kind of have gone through this once, what we're going to do is we're going to go through another example and figure out what forces would be experienced in that substance. So in our next substance, we are going to do the example of HNO. So HNO. Now remember our steps. Our first step is we need to draw the Lewis structure. So the Lewis structure, I'm going to go fairly quickly here, is going to have nitrogen in the center. It's going to be actually double bonded to an oxygen, and then single bonded to a hydrogen, and then have a lone pair on the nitrogen. Now, if you don't understand how I got there, that probably means you need to go back and review Lewis structures, so make sure you do that. And then what we need to think about next is, okay, well, what are the what is the geometry of this molecule? So the electron group geometry of this molecule, it has 3 electron groups, right? A double bond, a lone pair, a single bond. That makes the electron group geometry trigonal planar. You then have the molecular geometry, because it has one lone pair, of being bent. So I'm going to redraw this really quickly. So you have nitrogen, oxygen down here, hydrogen down here, lone pair over here. And now let's think about the polarity. Well, you end up having, this bond is not going to be like a huge difference, but you end up having quite a big electronegativity difference here. The nitrogen is going to be slightly negative. The hydrogen is going to be slightly positive. You really get two totally different sides of this molecule. This is polar. Which then leads us to be able to answer the final question of, what are the intermolecular forces experienced by this molecule? So the intermolecular forces, well, number one, we know London forces. Why? Because there are always London forces. Now the next thing I want to point out here is you have hydrogen bonded directly to nitrogen in a polar molecule. We're talking about hydrogen bonding. Now, a lot of people then ask, okay, well, do I need to write dipole? I would personally say no, you don't need to, because the dipole itself is the hydrogen bonding. You may want to check with your instructor, though, to find out with them and see what they ask of you. But in my opinion, if there is hydrogen bonding, you don't really need to think about dipole, because the hydrogen bonding probably is the dipole, but stronger. So I usually don't have my students worry about that. Okay? So that's how we figure that out. Now, let's do one more really quick example. Let's do an example where we have sodium ions and H2O. So we have sodium ions and we have H2O. Well, I know right now I have a mixture. So really all I need to do is check and see, okay, is H2O polar? Well, H2O we know looks like this. And we've seen quite a few times, we know it's asymmetrical, it has different electronegativities, and it is going to be very polar. We also have sodium that has lost one electron, and so now it's positive. So what intermolecular forces can you expect out of this mixture? Well, number one, you can expect London forces. In this, the London forces are so weak compared to everything else, it doesn't really matter, but they are there. What else do we have? Well, we have something that's polar and has hydrogen bonded directly to oxygen. You have hydrogen bonding. But we also have a polar compound and an ionic substance. So in this case, there is ion dipole forces. It's the only time you can have ion dipole forces is when you have a mixture of an ionic substance and a polar compound. So this is how we actually identify the intermolecular forces that exist inside of molecules. Find, number one, determine the Lewis structure, then find the geometries, determine the polarity, and that'll tell you the forces. And that should be how you approach this. And if you have any questions, make sure you ask. This is a really important time to make sure you review and practice. And if you are at the point where you still cannot draw Lewis structures, that's got to be your first step. That's like the foundational skill right now in order to help us answer all of these questions. Okay, so good luck. Thanks for watching, and I'll see you in our next video.